Why didn't it? Oh, crap. All right. You guys hear me okay online?
I can hear you.
Yeah.
I can't hear you, though.
Yeah, we can hear you fine.
Yeah,
guys-
we can hear you.
All right. Okay, good. I had somehow turned off my speakers. Okay. All right. All right. So before I get started, any questions anybody had asked online? Because I just wasn't hearing anything. My speakers were off. All right.
Mostly just attendance questions.
Yeah, hopefully you guys heard what I said there. I didn't hear what you said, but I updated the form after I sent it out. If you got the updated one, put your first name and last name. Otherwise, just put it all in the first thing and then click option 1. All right, sorry about that. All right, so where we ended up last time, talked about this idea of complex power. All right, and we basically said, first of all, let me ask this: power, P of t, power is a function of time, right? It's not a constant. In DC circuits, it's a constant. But what's it look like when I'm looking at an AC circuit? It's not constant then, right? What's it look like? It's a sine or cosine. And what's the frequency of it? What's the frequency of that sine or cosine?
Omega.
Well, how's it relate to the frequency of the voltage?
It's to the frequency of the voltage, isn't it just the frequency of the current plus?
It's twice the frequency, right? This is what we looked at. Okay, if I have a resistor, the current and voltage are always what? What do we say the current and voltage are when we have a resistor? They're in phase. All right, current and voltage are in phase with each other. And if I have a pure capacitor or a pure inductor, then what's true about the current and voltage phase then?
Shifted by 90 degrees.
They're shifted by 90 degrees, either forward or ahead, depending on it, right? So when I looked at an inductor, I had a 90-degree shift. And I still have this double frequency thing here going on, right? So that power is twice the frequency. But what's true about the average value there? What's true about the average value of that waveform? It's 0, right? But we said we needed to have a name for that. So what was the name we gave for the power that was going, or for the, to be clear, what's the name that we give to the element that's going on there? It's not power. We don't call it power. What do we call it? Reactive power. Reactive power is what we call it. So active power is power. Okay, so one thing to be clear about, I won't talk too much about the P of t, right? We really don't talk about that very much. We talk much more about P, which is the average value. Okay, so we gave sort of the formula for this. The formula is this guy that I've got right here, right? So P of t has an average value, plus it has these two double frequency terms. And the coefficient on the sine we call reactive power, or Q, all right? And what we did was we looked at this, we said, well, look at the coefficient on this guy, and I look at the coefficient on this guy. So I got a number times cosine of an angle. I got number times sine of an angle. What's true about that? If I have a number times a cosine and a number times a sine, those look like the two components of a what? A complex vector, right? Two parts of a vector. So what we did was we defined essentially for ourselves this guy right here. We defined the complex power vector, we call it. All right. So the complex power vector is this guy here, S equals P plus JQ. All right. And this component here is what we call P. This component is what we call Q. Okay. And the angle is the angle between the voltage and the current, or the angle of the impedance. And how are the angle and the voltage and current related to the impedance? Well, through Ohm's law, right? Angle of V equals angle of I plus the angle of Z, right? So this is just a rearranging of Ohm's law. So what we also said was, we said, well, that looks like the same thing that would happen if I multiplied V times I conjugate, right? Was what we worked through last time. So basically where we got ourselves to was this sort of summary, all right, last time, where we basically said, we defined a couple of terms, all right? We defined the term, so the complex power, which I guess I haven't written out here, is a formal definition, but the complex power is the P plus JQ, okay? The real part of that is the real or active power. Sometimes we just call it power, okay? The reactive power is Q, all right? And then we define this term called the power factor, okay? And we said all of this relates by saying, well, this guy right here, this complex power, can be defined as V times I conjugate, okay? And this table here, plus another table we're going to look at today, really summarizes everything, okay? So you don't need to get too bogged down in it. Just remember that these formulas are the truth. Now, the other thing we talked about is this idea of the units, right? So they have different units. So apparent power is the magnitude of the complex power, okay? That's given units of volt-amps. Power is given units of watts still. VARs is the unit we give to reactive power. And power factor is just the cosine of the angle here. It doesn't have any units, okay? Now we use some additional terminology to go along with power factor, which we're going to use here in a little bit, all right? But this is the crux of what we need, all right? Now, I've already seen some questions I wasn't able to respond to going on in the chat earlier today about peak versus RMS. Make a choice at the beginning of the problem. Are you going to do peak or are you going to do RMS? Generally speaking, do RMS, okay? Just make a choice, stick with it. If I ask you to switch between values, then switch, right? But essentially, make a choice, do the problem that way, all right? And use the right set of formulas. Usually people use the RMS. All right, we're going to do problems today in RMS, okay? Questions about that? All right. So we also started talking about, well, I guess at the very end, I introduced the idea of power factor last time. We looked at a really simple example. All right. So a couple of things, there's some more terminology that I want to throw in here just to add more terminology, right? So we got our typical loads, which are resistors, inductors, capacitors. Usually our loads are some combination of R's, L's, and C's, okay? They're not just an R, an L, or a C. All right, so I'm going to go away from that slide for a second and ask the question, and I'll go online first. What's the angle of the impedance if I have a resistor?
0.
0. What's the angle of the impedance if I have an inductor?
90.
It's still
90.
90. How do I know it's 90? So J omega L. So what's the J mean? 90 degrees.
That's your degree.
90 degrees, right? Because a vector that has just imaginary part points straight up. That's 90 degrees. If it was just real, it's pointing just along the real axis. So that's 0 degrees or 180. But for a resistor, you're never going to have a negative resistor. So resistor is always going to be 0. What about a capacitor? I have 1 over J there.
Negative
Negative
90.
Negative 90, all right? So if I just have combinations of R's, L's, and C's, my angle is always going to be between what angle and what other angle? 90 and negative 90. I'm never going to have an impedance that manages to be over in the second or third quadrant. It's always going to be in the first or the fourth, okay? And in general,
Does that have to do with like the load being inductive or capacitive?
it does, right? So if I look at this picture I've got right here, right? So impedances in the first quadrant are always going to have an R plus J omega L to them, all right? Anything in the fourth quadrant is going to have an R minus something. So if it has a minus, that tells me it's got a capacitive piece. It's got a positive on the imaginary part. It's got an inductive piece, right? So essentially what we see is in general, right? If I have an inductive type of load, the angle of impedance is always between 0 and 90. Capacitive type load, it's always between negative 90 and 0. All right, and we always have one of these sorts of things. Now, I mentioned this, in this class, we're not going to have negative real parts. This can happen in electronics. All right, it's not just, you can have negative resistances. All right, but that requires magic. All right, which means you need to have an active circuit. There needs to be some power flowing into that circuit to make that thing happen. All right, with the stuff we have, we will always be over here in 1 and 4. Okay, so a couple of things about that that leads to some terminology stuff. All right, so if I have an inductive load, all right, So I've shown out here, right? So my situation here, if I have a voltage, and let's just do this. In this case, if I had a load Z equals R plus J omega L, right? What we know is V equals I times Z. That is our statement of Ohm's law. Okay. So what does that mean? That means that phi V equals phi I plus phi Z. Okay. Where's the current going to be relative to the voltage? Well, so basically, if I look at this, phi Z is always the angle between them, right? Phi V minus phi I. If phi Z is always somewhere between 0 and 90 degrees, right? Let's say it's 90 degrees, all right? Let's say phi Z is 90 degrees. So 90 equals phi V minus phi I. Where is phi I going to be? Where is the current going to be relative to the voltage always? 90
Just be
degrees.
the negative.
90 degrees apart, and in particular, which direction? It's going to be behind, right? So effectively, what you're going to see, like, so let's say I had a pure inductor, right? So I had 90 degrees, and let's say phi V was equal to 30 degrees, which is about sort of what I have drawn in this picture right here. What's that put phi I at? Negative 60. Okay. So it's behind, we say. The current is behind the voltage. And so we call it lagging. All right. Now, what that would mean in terms of the time domain, if I looked on an oscilloscope, is if the voltage looked like this, the current would look like that. It has its peak later. All right. So it's lagging. So in this particular case, all right, that complex power vector that I talked about up here, right? The angle of that complex power vector is phi sub Z. Okay. So in this case, what we're going to say is, that's why we're going to do some examples here. We'll come back to your question in a second. So what I say is, if I have an inductive type of load, I say that this load has a lagging power factor. Okay. Meaning that it is a lagging type of load. It is an inductive type of load. It's phi Z, its angle is going to be positive. So the angle of the impedance is positive. So when I draw the S vector, I'm going to say the S vector is up here. All right, and this is going to be my P, and this is going to be my Q. So in this case, what's true about P and Q? Are they positive, negative, what?
Both positive.
Both positive, right? When terms in power are positive, like I have here, active power is absorbed, reactive power is absorbed. So they're acting like loads. They're absorbing power in both cases. Capacitors are going to be the exact opposite. All right. For all the same reasons that we just argued that it was that we made here, everything's opposite for a capacitor, because what's different about the angle of a capacitive load versus the angle of a inductive
It's
load?
negative.
Negative, right? And so that flips me over, all right, into this situation. So capacitive loads, we say, have a leading power factor because the angle is ahead. All right, that means that the current has a peak before the voltage if we look in time. Okay, that's an earlier peak. So we say that these guys have a leading power factor. Okay, is the term we use. Now, in this case, what that means is if my phi Z is negative, that means my S vector is here. Here's phi Z. So here's P, here's Q. What's true about my P and Q here? So P is positive. What about Q, though?
Negative.
Q is negative. That means this guy is effectively a source of Q. All right. And that is, in fact, the way utilities use capacitors, because for the most part, most of the loads that exist in the real world are inductive loads. All right, so motors, you think the majority of loads in the world are motor type loads or resistive type of loads. So it's heating, air conditioning, all that kind of stuff, right? Lights. For the most part, those loads are inductive loads. All right. So utilities will put capacitors out there to maybe help with those loads, all right, to source things to those loads. All right, so we have this term leading power factor, lagging power factor. And so in summary here, right, I kind of think of my stuff like this. So if I have an inductive load, right, if I'm looking at a load, the impedance angle is somewhere between 0 and 90. It's absorbing power, so P is greater than 0. It's absorbing Q. We say that I lags V, all right? And then for a capacitive load, we say I leads V. So we got a good summary of all that there, all right? And then we can make some other relationships if we need to, right? We can make some other relationships I don't want to hit on today, but I can go back and I can do some stuff with respect to V squared over R and V squared or I squared R. I'm not going to touch on that today. What I want to kind of point at is to get into some problems, which is to say, if I want to summarize everything, this is kind of the key summary of it all right here, this slide. It's the last slide, the 59th slide, I think, of the notes that I posted the other day. All right, it's probably the only one you'll ultimately care about, slide 59, maybe the one before it. All right, and it basically has in there all the relationships that we need. What does it mean to be an inductive load, a capacitive load, all that stuff, and those are our key relationships that we'll need to figure out apparent power, real power, reactive power, complex power. All right, questions? Eli, you had a question. Maybe you don't even remember what it is anymore.
I've answered already, like, it's just the way I wrote in my notes, but I was gonna ask, like, it was 0 and 90 relative to what angle Z with phi Z?
Yeah, phi Z is the angle that we're really talking about here. All right, so let's look at an example. Okay, so here's the situation. I think this is probably like problem 5 or 6, not 2.
Oh, wait, no.
2 should be easy, I hope.
I'm
I hope.
something wrong there. But...
All right. I hope it's easy. It may not be, right? But the later problems, if we can do this, you can do the earlier problems at least. So I threw out a bunch of stuff. I made this guy up. I said I got 2 loads. Load 1 is absorbing 15 kilowatts at a leading power factor of 0.92. So I went straight into those words that I was using. And load 2 is absorbing 20 kVA at a lagging power factor of 0.85. That's a pretty common way that people will refer to a load, is they'll say how much, what's the power and what's the power factor. Now the problem with the power factor is a cosine of an angle. So it doesn't tell me whether or not I've got positive or negative, right? Cosine of a positive angle, cosine of a negative angle are both positive. So I throw in this leading or lagging term to make things clearer, okay? All right, so I need to check here. I threw one other value in, 200 micro, okay. So LS, this inductor over here, is 200 microhenries. And my frequency is 60 hertz. Okay. All right, so there we have it. That's my whole setup. So I'm saying I have a bunch of things that I want to figure out. I want to figure out all these values here. Let me do them in a slightly different order. V1, V2, complex power from the source, and I also want to determine V sub S, like that. All right, so we got a couple of things that we need to figure out. So we're going to go through that process. So where do I start with this? Find I2, yeah. Tone, you're not supposed to start me with a smart ass answer. Tone already knows what I2 is, right? All right, so where do we start to figure out what I2 is? Well, so you're talking about for the transformer?
Yeah.
I'm going to need that eventually. So I'm going to need to figure out those ratios. So might as well, in fact, let's figure out our ratio stuff now. So if I look at the transformer picture here, all right, so I've got, all right, let's draw that by itself. 3 to 1 was my ratio. and V1 and V2. So, and I've given you definitions. I1 is going this way into the dot. Here's V1, here's V2, and here's I2. Those are my definitions that I've given in this problem. Okay. So what did I say? When I start with this, I got kind of a 3-step process that I kind of go through. First one is to get the voltage relationship here. Okay. So it's always true that the absolute value of V1 over N1 is equal to the absolute value of V2 over N2. Always true. Okay. And then we said there's a sign issue I got to worry about here, right? So in this particular case, it is positive and positive. Why is that? Both the dots are on positive. Not necessarily they're in the same place, but they're both on positive. Like they could be flipped over. Like I could have a dot up here and a dot on the bottom. But as long as the plus signs are both at the dots.
But if it's the same, they're both on the negative, right?
It's the same if they're both on the negatives, right? If yeah, then it would also be. So they would only switch if I had a plus sign on the dot on one side and a plus sign at the opposite of the dot on the other side. If I had changed this so that I had plus here and minus here, then I would have had a negative. If I had flipped them both, it would have been positive. All right. Coach was thinking about what I might do on a test.
What does a dot actually mean?
Yeah, so it's a good question. So it's without this is where labs would really be helpful, right? If I had a dot, if I applied voltages like this, what I would see is if I put a voltage source on one side and measured the voltage at the dot on the other side, the voltages would be aligned up with each other. They'd be in phase with each other. If I put my oscilloscope probe at the negative terminal on V2 and my function generator red terminal at the positive terminal on V1, they'd be 180 degrees out of phase with each other. And that might matter. If you screw up the way you wire up a transformer, you can cause your loads to blow up or do various different things, right? So it does matter how you wire those. If I just gave you a transformer, you'd have 4 leads coming out of it and you'd be like, which one is which? So that's how you figure out. The dot convention allows us to figure out which one is which. All right, so I got that relationship. I'm gonna need it. All right, I also need to get my I relationship. All right, so the way that I do that is I say I write my power relationship. I say P1 plus P2 equals 0. And I figure out, well, is P1 positive, P2 negative? All right, so P1 is basically, in this case, V1, I1, right? The power is going into the plus sign, so I write that as positive. What about on the other side there? What's
It'd be
true?
negative.
Be negative, yep. So I got negative V2, I2. Why is it negative?
Because your current's coming through the negative.
Yeah, my current, well, because my current's coming out of the plus terminal and into the negative terminal.
Yeah,
I think.
that's what I meant.
Yeah. So that means then basically I get V1, I1 equals V2, I2. Okay, so that's good. How do I solve this to get a relationship now? What do I need to do? Yeah, so I plug in V1 and substitute for V2, right? So V1 equals what? Yeah, so I'm going to say N1 and N2 over V2, yeah. Right. It also, in this case, is going to be 3 if we want to do it that way. V1 equals 3 V2. Okay. So then that tells me I'll substitute 3 V2 times I1 equals V2 times I2. Right. The V2s cancel, and I have that I1 equals I2 over 3. Okay. So what's that mean? That means that the voltage on the primary side is 3 times bigger. So that means that the current on the secondary side has to be 3 times bigger, right? So basically the side that has more voltage has less current. The side that has more current has less voltage, but they always the powers are matching each other here, right? So if I have 400 volts on one side and it's a 10-to-1 transformer, the other side is going to have 40 volts. But the side with less voltage is going to have a heck of a lot more current. All right, that's the whole idea. questions about that?
Can I just say I1 times N1 equals I2 times N2?
You could, so what's true is this, V1 over N1. This is true always. And I don't even know that I can say that. Yeah. That's true always. The signs may not. The trick is the signs, right? That's why I go through this process, is to track the signs. Okay. You're right. I mean, in terms of the absolute values of everything, yeah, that is a true statement. But the signs are the part that's tricky. All right. So to back up for a second, so you guys got the relationships that we need. All right. In any of these problems, I like to think of it like this. Sometimes they call them power triangle problems. Okay. Because you got a vector, and so it looks like a triangle, right? And because it's always going to be in the first or second quadrant, it is really just like a triangle. Sorry, first or fourth quadrant. All right, first or fourth quadrant. 3 steps. Basically, you're always going to be given 2 sets of quantities, right? I need 2 things to get 2 things to be able to figure this out, right? So, like it says here, usually you're given the magnitude of S, which is what now? What's the magnitude of the complex power? What name did that have? Anybody remember? Anybody online remember what that is?
The quantitative power?
It's
Or
the
the reactive?
the apparent power is the magnitude of S. The magnitude of S. P is the real power. Q is the reactive power and power factor. You're given some. You have to be given 2 of those things. Any 2. All right. Any 2 is enough to figure out everything else. All right. Then basically, I usually have to figure out whether my phi z is negative or positive, right? So if I'm told that the load is leading, then it's capacitive. If I'm told that the load is lagging, it's inductive. All right, and then I basically got to use trig to figure out everything, and then it's a matter of sliding through those formulas. Okay, so that's what we're going to try to do. So you guys figured out, or we figured out together, that we've got these 2 relationships we're going to need in this problem. All right.
What was step 2? What was step 2?
Step 3 was to chug through the trig to figure it all out. So we'll go through the steps here. All right. So really, to begin this problem, I said I want to figure out I2. So to figure out I2, I got to start with my steps there. I got to go in and I got to figure out the complex power. So load 2 is over on the secondary side. I'm going to start with load 2. All right. So for load 2, all right, how do I approach this for load? Well, so yeah, let's figure out what we know. I said I needed to be given 2 things about the load, right? And I was. So load 2 absorbs 20 kVA at a lagging power factor of 0.85. Yeah, 20 kVA at that. Now you'll notice, I saw Fish, you were saying this in the Discord. Most of the time these things are going to be K or mega, kilo or mega, and you may get caught up by that because it's meaningless to talk about power at 100 watts, right? If you have 100 watts for an hour, Duke gets paid a penny for that, right? So it's meaningless stuff. So oftentimes when we're talking about problems, we talk about 100 kilowatts, 100 megawatts. You know, so often those units are going to be a lot bigger. Okay. So pay attention to that. You may start getting stuff wrong, thinking you're right, and I'm asking for it in kW or kVA or megawatts or whatever. So read those problems carefully. I sense that some people have already lost an hour of their life because of that. All right. Yeah. Yeah. All right, but it's common that we do it that way because again, power tends to be in kilo or mega values. So all right, so we still haven't started the problem yet. So I2, all right, so load 2 absorbs 20 kVA at a lagging power factor of 0.85. All right, so I'm going to go to my summary slide here. So kVA. All right. So which one's VA here? Apparent power, which is not the complex power. It's the magnitude of S. All right. It's the magnitude of S. So we're told that the magnitude of S, so for load 2, all right, we're told that the magnitude of S equals 20 kVA. All right. And that's probably how I'm going to give it to you on the test too, is I'm not going to tell you that, well, the apparent power is this, or I'm going to tell you this is kVA or kVAR or whatever. And it's going to be up to you to figure out which one that is. Okay. Now you're also told that the power factor is what? Is 0.85 lagging. 0.85 lagging. All right, so I said step 1 of my process is to figure out what 2 things I've been given. And those are the 2 things I've been given. All right, so what I need to do next, sort of my second step, is what does it mean to be lagging? All right, well, what does it mean to be lagging? Let's go up to my summary here. All right, so that really gets into the type of load. Here, lagging or leading talks about the type of load I'm dealing with, right? So inductive load, my angle is between 0 and 90. Capacitive load, I'm between 0 and negative 90. All right, which one do I have here?
Inductive?
I have an inductive load. I lags V. So I call it leading or lagging based on what the current's doing. So I lags V, I leads V in a capacitor. So if I have a lagging type of load where I lags V, then I say I've got an inductive type of load. And so what does that mean? This is the tricky part. That means if I were to do this, all right, I was told that the voltage across that load is 480 volts with an angle of 0 degrees. So in that case, that means I got 480 like this. This is the voltage like that. Where is the current?
In quadrant 4.
Quadrant 4. Like that.
No, it's quadrant 4, never mind.
It's quadrant 4. Yeah. All right. So my I is over there. So that means phi I is down here. Phi I better be somewhere in that quadrant. That's my lagging load situation. Now, what does that mean about my S though? My complex power vector. Where's that going to lie? What's the angle of S? Let's go up here. So here's my S as a magnitude and an angle. What's the angle for that guy?
Would it be inverse cosine of the power factor?
I like that.
Well, it will be, but let's not go straight. So
It's phi z.
the angle, you're right. The angle of S is always the same as the angle of what?
It's the angle of voltage subtracted by the angle of current.
The current, which is the same as the angle of the impedance. All right. Power factor is just a number. That's what I'm saying. There's lots of terms here. We get lost in those terms pretty quickly. The S vector, the angle of the S vector is equal to the angle of the impedance. All right. This slide's got it all. All right. Basically, you go through this and you got what you need. All right. So angle of Z, which is, as Gideon said, is correct, is angle V minus angle of I. Okay. It's the angle of the impedance. So we determined here that this was an inductive load. That's what this lagging term meant. Okay. What's true about having an inductive type of load about its impedance angle?
It's between 0 and 90.
0 and 90 is quadrant 1. So somehow I know that S is over here. Here's my magnitude of S. Okay. Here's Q. Here's P. And here's phi Z. I need to know that to figure out, because my other load's going to be the opposite. I'm going to need to know. I'm going to need to know whether it's capacitive or inductive. All right. So now what I want to do is I want to go through for load 2 and I want to figure out P and Q. Okay. So how do I do that? How do I figure out P and Q? Musa, I'll go back to you. You said something there about the power factor. What's power factor equal to?
It's the inverse cosine of the, oh, sorry, power factor is 0.85.
Yeah, and it's the phi
Cos-
z is that. Cosine of phi z is the power factor, and this is 0.85. So that tells me right there to get how to get to phi z, right? Phi z is the inverse cosine of the power factor. Now, I didn't write that down as a formula because that's not always true. It could be the negative inverse cosine of the power factor. All depends on whether I got an inductive load or a capacitive load. All right, that's hinted at in this summary slide, all right? So we got some work to do to figure that out. All right, so we see here power factor is cosine phi v minus phi I, all that kind of stuff, all right? So I can calculate that phi z, then how do I figure out P and Q for myself? All right, I'm going to call this specifically P2, Q2, because this is for load 2. Like that, all right? So Q2 and P2, what do I do to get those now? Magnitude of S times cosine phi z. So technically I don't even need to compute the cosine, I already have it. It's 0.85 is the cosine of that angle. Q2 is going to be what? Yeah, sine. And again, all the formulas I need are sitting out for me right there. Now, the one thing is the magnitudes, I guess I didn't write it as magnitude of S, but you can extrapolate that, hopefully. All right. So that's my S2. So if I want to figure out what my complex power vector is, my complex power vector would be S2 equals P2 plus J Q2. That's my complex power vector now. All right. Christian, you had a question.
When we do the phi z equals cosine inverse of 0.85, is that going to kick back an angle like a degrees or radians?
Definition always radians. All right. By definition, it's always radians. So there may be in Matlab there may be an A cos D. I don't know. But the thing, like I said, in my mind, what I always do is I keep it all in radians because I know that everything wants radians. Okay. So, all right, I wrote a little Matlab thing to try to approach this. All right, so let's put them side by side. Okay. So I put in all the information I had. Power factor 2 is 0.85. S magnitude 2, my apparent power. All right, so we can call it that, apparent power for load 2. Okay. I put my turns ratio information, my impedance information, all that stuff. And I put that phi Z2 was negative A cos power factor. So if I want to get inverse trig functions in Matlab, it's arc tan, arc sine, arc cosine. So A cos, A tan is the way that's written out. So then I wrote out my P and my Q stuff here, right? Just like I did over here, right? I'll give you guys this file, right? So these two go together, and then I put them together into one vector. So let's see what I got when I did that.
What's that con J?
No, let's not worry about that yet. Let's just step down from.
Positive, negative, A cos.
That's for. That should be positive. Let me make sure I did this right. Yeah, load 2 has a lagging power factor. Right, so if I had a lagging power factor, that meant my impedance was up in the first quadrant, right? So I'm over here, okay? And I get this result right here. All right, so let's run that. And okay, there's my S value that I get here. So what this tells me is, so P2 says is 17,000, Q2 is this ugly looking number here, right? So what does that mean? So I'm going to write this out. So that's 17 kilowatts, right? And then what do I say for my Q there? That would be plus J times what? So that's 1 times 10 to the 4th is what? 10
10,000.
kilo.
1053.6.
Yep, so I would say this guy is 10.536. That's how I'm gonna write it. And what are the units gonna be?
No.
So if you're not sure, you go back to the table there.
Bars.
Yeah, so for Q, the units are vars, volts, amps, reactive. All right, so that's gonna be K var. All right, KW and K var. Okay. All right, so I got that down. All right, so now still haven't even really answered the question it asked us, which was determine I2. All right, what is I2? Well, I2 is the current going into that load. What do I know to figure that out? I don't have an impedance here, do I?
So don't we have the impedance due to the capacitive load? Isn't Z just R?
First of all, it's an inductive load, right? But second of all, I don't know anything about the impedance. I know that it's inductive. I know the voltage, right? I know the voltage is 480 volts. Okay. But I don't know the impedance. I know the impedance angle, but I don't know its magnitude. All right.
Well, if you know,
yeah, go ahead.
if you know S and you know V, you can find I.
If I know S and I know V, I can find I, right? Because the other key relationship we had here that we looked at, right? The other key relationship I've got is S is V times I conjugate, and that's P plus JQ. So we know what the voltage is. We know what P and Q are. So we can do it from there. Okay. So that tells me, right, if I go to move this out of the way, right? So S2, which we just determined, is equal to V2 times I2 conjugate. All right, V2 times I2 conjugate. It was just a pure math thing. There was no physics relationship that happened there. We just basically, somebody looked at that P plus JQ and said, well, that looks like what would happen if I did V times I conjugate, right? And it is. So in this case, I know what V2 is. We just solved for S2. V2 is 480 volts, and the angle is 0 degrees. Okay. And then I'm solving for I2 conjugate, like that. All right. So what I can say then is that I2 conjugate is equal to S2 divided by V2, like that. And if I want to know what I2 is, what is that?
It's just
I2,
the reciprocal.
not the reciprocal.
Oh, sorry, it's just negative, right?
I take the conjugate of both sides, right? So it would be S2 V2 conjugate, like that, right? Conjugate of this side would be the conjugate of that side. So I could just do it that way.
Could you do it where you plug it into Matlab and then you split the sign and the imaginary part?
Oh, that's the conj function, right?
Yeah, I mean, I could flip the sign of the imaginary part. There's a couple of different things I could do. Yeah, there is. So there is. You could do it manually, like you're talking about, right? So what I did here was I said it's the conjugate of that term.
That's a nice function.
Yeah. Like I said, MATLAB knows what you're thinking. It has a function for that. That should be the slogan. There's a function for that, right? So I've got my I2 now. All right. So now if I run this guy, now let me ask, before I ask this, where should the angle of that current be? Because I want to check to make sure we're right. Where should the angle of that current be? This guy was a lagging power factor.
Quadrant 4.
Quadrant 4, right? So we said it should be in quadrant 4, so it better be, oh, look, it is. All right, I got a positive real part. I got a negative imaginary part. It tells me I'm over in quadrant 4. All right, so in particular, I've now got my I2. So my I2 I've determined now is 35.4 amps minus J times 21.9495 amps. Okay, now no one in their right mind ever says I got so many negative imaginary amps over here. This is given as a phasor, right? So you would say, what's the magnitude and what's the angle of that? Okay, it's how you would enter that. Okay. Now, one thing I didn't mention at the beginning of this, but I said, unless I tell you otherwise, everything's RMS. All right, so everything I'm doing here is an RMS number. So if I had said to you, all right, what's the peak value of the current? Yeah, well, and I would multiply by the square root of 2. All right, is how I would figure that out. All right, if I ask for the peak value, but unless I tell you otherwise, we're talking RMS. All right. All right. Questions up till there?
So if you find the IMS, I2, can you find the absolute value of P S divided by VS?
So yeah, the question, so I could have looked at this problem, I think, and to find the I value, I could have said the magnitude of S is equal to VRMS IRMS. That would have worked too. All right. I know VRMS and I know the magnitude of S2. Then I would have had to find the angle separately. But yeah, that would work too. So what he's saying is, because we knew, right, we knew that the magnitude of S was 20 kVA, and we knew that that was equal to VRMS IRMS, right? I could have solved for the magnitude of the current, and then I would have had to have said that phi Z equals phi V minus phi I, and I knew what phi Z is, I knew what phi V is, and I'd have to solve for phi I. Right, that would still be true in this case, right? And I could run through that if you guys want to see it, but if you try it, you'll see it later. Okay. All right. So we got that. We got more to this question. So let's go back to the original question. All right. So I said determine I2. Now I want to know I1. All right. So looking at this picture, where is I1? How would I figure it out? Yeah, so I1 is the current into the primary of the transformer. I know I2, the current into the load, is the secondary of the transformer, right?
Couldn't you just use the terms to just find them?
Sure can, right? So we figured out that I1 is equal to I2 divided by 3. All right, and so that means that in this case, if I want to do this in Matlab, okay. All right, so I1, so there's what I did there. So I1 equals N2 over N1, which is what we found. And V1 is the same sort of thing. So I can get the voltage and current over there pretty easily. Okay. All right, so that's how I approach that problem. Pretty straightforward. We already got a relationship there. Now, the next question basically refers to what's going on with load 1. All right, load 1. So load 1 is this guy over here. Okay. So I want to figure out, it says determine the total complex power flowing into the load combination. So I want to figure out first, I want to figure out the power going to load 1. Okay. So let's get the complex power there. So load 1 absorbs 15 kilowatts at a leading power factor of 0.92. Basic power triangle process now again. I've been given 2 things, and now I got to solve to figure out everything else. Okay. So what 2 things have I been given in this case? Power factor is 0.92, and the active power, right? I was told the kilowatts. So I know P, and I know the power factor. Okay. Now the fact that it's leading, I go back to my chart, right? So in my charts here, I go to this first chart, right? I got to figure out whether that's an inductive or capacitive load. Okay. Which one is it? If it's a leading power factor. Leading power factor, it's a capacitive load. All right. So that means that if it's leading, I leads V. I leads V. All right. So I'm going to draw my picture here. So if I'm talking about load 1, and let me just go back to.
So in transformers, when we're either leading or lagging, it's always with respect to.
Transformer has nothing to do with this, is whether the load's leading or lagging, right? So transformer is not the load. Transformer is just a thing sitting between the two loads, right? So when I'm talking about load, in this case, the way it's set up is load 1 is in parallel with the primary. I got a load 1 right here. He's in parallel with the primary, and I know with that load 1, I have, what did I say? I got 15. So P is 15 kW. He was a power factor of 0.92 leading, which meant that this was capacitive. All right, so let's figure out as much as we can about that at this point. So if I'm talking about the relationships between the voltage and the current, looking at the original picture, V1 is the voltage across that guy, right? V1 is the voltage across that guy. What's the angle of that voltage? Same as V2, right? V1 over N1 equals V2 over N2. There's no change in angle that's going to happen there, right? So I know that the angle of that's got to be 0, right? So V2 is here. Where is I, the current here? Or sorry, it's not V2. This is V1. All right. The current, I'm just going to call this I. All right. Where is that current?
First quadrant.
That current will be in the first quadrant. Yep. Because it's a leading power. I leads V. So its angle is ahead. All right. So what does that mean about the power triangle? Where's it going to be? What's the angle of the power triangle thing? What's the angle of the complex power vector?
Negative 90 to 0.
Yeah, so the thing to remind ourselves, the angle of the complex power vector is the angle of the impedance. If I have a capacitive load, yeah, it's going to be between 0 and negative 90. So that means the angle of this guy is going to be a negative angle, right? So that puts this thing, where's my picture? Here's my picture. Right? My S is going to be over here. This will be my S. This is theta Z, or sorry, phi Z. This is P. This is Q. All right, so my Q is going to be negative in this case.
Dr. Cox,
Yep.
I was wondering, how is it possible that it leads, but yet it's saying it's absorbed?
That it's so what it says is it's absorbing 15 kilowatts.
Got it.
Okay, so you're always absorbing P.
Okay.
Yeah.
And you can, okay, that makes sense.
Yeah. So it's sourcing Q and it's absorbing P. Loads are always going to absorb P. Okay. All right. So I've got that relationship. So now what do I do here to figure out what's going on? Well, so I know P, I know the power already. Let's say I want to figure out the whole vector. So it means, what do I need to figure out? I got to figure out Q1. This is P1, Q1. So I'm going to have to figure out phi Z, right? So how would I figure out phi Z1?
The negative cosine inverse of.
Yes. Yeah. So we know that the power factor in this case, right? Power factor is always cosine phi Z2 like that. But in this case, I would say that phi Z2 is equal to negative inverse cosine of the power factor. Power factor is always stated as a positive number because it is, right? All right, so the power factor is always stated as a positive number, but I may have to put a negative in this based on this wording, whether it's leading or lagging. So you read the wording to figure out which it has to be, whether it's leading or lagging, okay? So in this case, negative cosine inverse of the power factor. All right, so then I can figure out what that is. So what would I do? So I know what P is. So to figure out the complex power in this case, what do I got to do now? Next? Somebody online, what's my next step to figure out the full vector S1? Well, I have P1. What do I need to do now?
Find Q.
Find Q. All right, so J Q1. And what's Q1? How would I figure that out?
S1 over P1 or minus P1.
Well, I don't know S here, right?
RMS times IRMS times sine of phi z.
Yeah, so here's my formulas, right? So my thing is at this point, well, this guy's a vector, right? So I just should think of this in terms of trig. All right, I know P. I know this angle. If I wanted to find this vector over here, Q1, that component of the vector, it's like a triangle. That's why we say it's a triangle problem, right? So how can I use my trig to do that? What do I know about trig to get me to what Q1 is there? Yeah. So I could figure out S, but I mean, I don't know what S, I don't know what the magnitude of this vector is just yet, right? Do what? You say did you say cotangent?
Yes, sir.
I thought you might. Tone wants to use the cotangent. Anybody want to use the cotangent? I don't want to use it. Yeah. Tangent of, I haven't heard that term since in a while. Tangent of phi z equals, let's just do the tangent, right? What's the tangent?
Opposite over here.
Q1 over S.
Q1, not Q1 over S, Q1 over P1 like that. All right.
Oh.
And then I can solve for it that way. All right. Or I could do the cotangent too. Yeah. Cotangent would be the opposite of that. Well, let's skip that one and do the cosecant next. Yeah. All right. Kojo, yeah.
This one is going back a little bit, but why is the magnitude of S?
So in this case, we're saying the vector points downward because I have a leading load. Leading loads are capacitive. Capacitive loads have a negative angle. And the angle of the vector is always set by the angle of the impedance. So I is positive, so the impedance goes negative. And I mean the vector, the complex power vector follows the impedance. Once you see there's a process and you keep flipping back that summary slide, eventually this will get super easy, right? But it's a process and it's getting yourself comfortable with the steps in that process, right? All right, so when I look at this, so then I can solve for my Q1. My Q1 is going to be P1, which I know, times the tangent of phi Z1, like that. All right. And then I got my Q1. All right, so let's do that. I don't think I actually wrote that into my code, but I can. All right. So let's do that second load. So I was told that the power factor 1, here's how I would enter it in. Power factor 1 is 0.85. Okay. And then how would I put in, oh, 0.92, sorry, I reversed them. 0.92. Okay. And then phi, how did I do it with the other? Phi Z1 is equal to, I said a cos of PF1.
Negative A cos.
And it's negative, right? Did that on purpose actually that time. I wanted to ask that question. Negative a cos, because remember, in this case he's leading, so negative because leading. Okay. All right. So then we said in this case my P1 was 15 kilowatts. I'm going to say 15,000. My Q1 is going to be this formula we had right here, right? So Q1 equals P1 times the tan of that. All right, so Q1 equals P1 times tan of phi Z1, like that. All radians, right? I didn't do any Ds. All right, all radians, because I know that all my trig stuff is that way. And I'm going to say my S1, that power there, S1 is equal to P1 plus J times Q1. All right, and there's my power. Questions about what I did there? All right. So I'm going to run that guy. All right, and All right, so there's my answers here. So
How did we already know the value of P1?
that that was in the problem statement here. So we were told that, oops, we were told that the load
Was
Oh,
absorbing
see it.
15 kilowatts at a leading power factor of 0.92.
okay.
Okay. So push this guy over here. Put my Matlab over here. Okay, so notice my Q1 is negative, right? So it goes down just like we said it would, right? So in this case, so the fact that it's negative means what? What does that mean? What does it mean to have a negative power of some kind?
supplying or source.
It's supplying it. All right, capacitors supply reactive power. All right, and that is a true statement. So basically I have my S1 vector is the 15 kW. What would I say about my Q there? So I'd say minus J times, so 6.39, what I have? 6.39 kVAR, not millibars. Yeah, millibars would be nothing. 6.39 kilobars, right? So, all right, now what I want to figure out is, to this picture, I want to know the current going in there. Right? Now we know that the voltage across it was V1, which we solved for with our transformer relationship. All right. So if that's the case, all right, what would the current going into that thing be? How would I figure out the current? We did a similar thing on load 2, right? Load 2, we knew the voltage. We don't know an impedance, but we do know power. So how do we do that then?
S1 over V1 looks like the conjugate of us.
So S1 equals what? So I can go back to my summary slide if I'm not sure, right? So S equals V times I conjugate, okay? So what I have there is S1 equals V1 I conjugate, like that, okay? And so thing that I do, so a couple of different ways we could solve two equations, right? One equation for the magnitude, one equation for the angle, or I can do them all at once, right? I could say that the magnitude of S1 equals the magnitude of V1 times the magnitude of I conjugate. Magnitude of I conjugate and I is the same, right? And so this would be one equation. Second equation would be the angle of S1, which is the same as phi Z1, equals phi V1 minus phi I1, or I minus phi I.
Is the angle of I1 same as the angle of I conjugate?
So I here, so notice the way I've defined this. I is the current going into load 1. There is a current I1, which is going into the transformer. So that should be clear. I'm referring to I being the current in this load 1. All right. V1 is the voltage across it, but I is the current into it. All right. Why is there this negative relationship here? Why did a negative come out here?
Or is it conjugate?
Count for the conjugate, right? Because if I said, what's the difference? What's the angle? If the angle of I is phi I, what's the angle of I conjugate? Negative phi I. It's the negative of that angle. Okay. So I can solve those two relationships independently if I want to as well. All right. We know phi Z1, we know phi V1, so we can solve for phi I1. What I did in my code is I said, well, it's also true in one step that I conjugate equals S1, this way, equals S1, the complex power vector, divided by V1, the angle of that voltage. And what I say is, and again, not I1, I, right? So what I say is take the conjugate of both sides. So I is going to be S1 divided by V1 conjugate of that result. All right. So in my code, all right, what I would say is for that I would say I equals the conjugate of S1 divided by V1, right? And that's how I would get my I. Now let me ask you this. Where is the angle of that load going to be? First quadrant or fourth quadrant?
Fourth.
So this is a leading load. Leading load means what? That's a capacitive load. In a capacitor, I leads V, right? So it's going to be the first quadrant. Phi Z is in the fourth quadrant, but the current is going to be leading the voltage, all right? That's why I'm saying don't study this slide, you know, to wrap your head around this. If I look at this, capacitive load means my angle is in the fourth quadrant for the impedance, but it always means that I leads V. So I is going to be ahead of voltage. My voltage has an angle of 0, so that's going to put I in the first quadrant, even though the power is in the fourth quadrant because of the impedance angle. All right, it is pretty neatly summarized, I think, there. Once you start to dive into those problems. So let's run that. All right, I run that, and there it is, right? It's in the first quadrant. All right, so in this case, my I is 10.4167 amps plus J times 4.4375 amps, like that. Okay. All right. Now, we're pretty much at the end here in terms of what we can do today, but let's talk about what else it asks me to do here. So we talk about, that should be enough to kind of be thinking through on the homework, basically what we just did. All right, to start thinking about the homeworks for next week, now I'm gonna say, well, all right, I wanna start thinking about what's the current going through here, all right? So how would I figure out so I wanna figure out things like, what's the total complex power coming out of that source? All right, so how can I think about what's the total complex power coming out of that source? Do KCL right here, right? I sub S is the current going right here. With that I sub S, I know what I is right here. I know what I1 is. So I can figure out what I sub S is pretty easily just by KCL, right? I sub S has to be equal to I plus I1. So I just add those together, all right? So that'll get me to the complex power coming out of the source pretty easily. So once I have that I sub S, how do I figure out the complex power coming from the source?
I sub S times V.
V sub S times I sub S conjugate is the power coming out of the source.
So when we do the KCL, we're getting the non-conjugate.
When you do KCL, you're just doing KCL for current, right? I can do KCLs for conjugates, I guess, if I wanted to, right? The same thing would be true. But if I know so in this case, I know I1, do KCL to find IS. Conjugate only comes into play when I'm talking about the complex power, specifically complex power, right? So those are all my steps. All right, so we're gonna go through. Key thing for you, go to the last like slide or two. It's like slide 59 or 58, whatever it is. That's really where you want to start attacking these problems. Approach them primarily in RMS. Don't start mixing and matching between RMS and peak unless I tell you to. Which probably in problems 2, 3, I probably tell you to go back and forth. But eventually, it's all RMS. All right. All right. So reminder, office hours is tonight